In this video, we're going to continue to talk about antiderivatives. We're going to give the formulas for the antiderivatives of some simple, basic functions, including power functions, sine and cosine, 1 over x, and e to the x. We're also going to establish some rules for antiderivatives, which are sort of parallel to the rules that we had for derivatives. Namely, we'll introduce the sum, difference, and constant multiple rules for antiderivatives. And then we'll have a look at some common errors that can occur when students are working with antiderivatives for the first time. Yesterday, we established several important facts. In particular, we established that if you're taking the antiderivative of x to the n, where n was not equal to -1, then the antiderivative of that function could be found by increasing the power first, and then dividing by the increased power. Now, in the specific case where n is equal to -1, n plus 1 doesn't make sense because it would make us divide by 0. When n is equal to -1, and we're looking at the special case of 1 over x, the antiderivative is given by a special formula. That's given by the natural log of x. We saw that in yesterday's exercises. Now, what if we have e to the power x? What function has e to the x as its derivative? As we know, if you take the derivative of e to the x, then e to the x is the result. So e to the x is not only its own derivative, but its own antiderivative. What about cosine of x? We also have the fact that if you take the derivative of positive sine, positive cosine is the result. However, we have to be a little bit more careful when we're finding the antiderivative of sine. The antiderivative of sine is given by negative cosine, because the derivative of cosine is equal to negative sine. So these are the building blocks for the antiderivatives that you will be taking in Calculus 2. The antiderivative of power functions, including the special case of a power of -1, the antiderivative of e to the x, cosine, and sine. Now, I keep saying the antiderivative, and I really shouldn't. It's just sort of a bad habit. In reality, functions are going to have multiple antiderivatives. Functions actually have infinitely many antiderivatives. For a quick example, let's consider the antiderivatives to the function f of x equals x squared. Now, the formula that we gave on the previous page says that if you increase the power by 1 and then divide by the increased power, you'll get an antiderivative of x cubed over 3. That function is definitely an antiderivative of x squared. But it's not the only one. For example, if you take the derivative of x cubed over 3 plus 1, then you're going to get the same answer. You're still going to get x squared because the derivative of 1 is just going to vanish. So x cubed over 3 and x cubed over 3 plus 1 are both perfectly valid antiderivatives of f of x equals x squared. So let's see if we can take the antiderivatives of those basic functions and find antiderivatives of more complicated functions that are combinations of those basic building blocks. Suppose we have two functions, lowercase f and lowercase g. And we know antiderivatives for those individual functions, capital F and capital G. If I want to find an antiderivative of the sum, f of x plus g of x, then I can find the sum of antiderivatives. Capital F of x plus capital G of x is an antiderivative of lowercase f plus lowercase g. The same thing is true if you subtract. If I want to find the antiderivative of a difference of two functions, take the two individual antiderivatives and subtract them. Likewise, the same thing is true of constant multiples. If I want to find an antiderivative of some number times f of x, all I have to do is take that number and multiply it by the antiderivative. So this vastly immediately expands the number of functions whose antiderivatives can be calculated. But do be careful. What we have not said is any way to calculate the antiderivative of a product or a quotient. As we recall, derivatives of products and quotients are generally pretty complicated. Antiderivatives of products and quotients are even worse, believe it or not. There are only a few somewhat finicky techniques that can, if you're very lucky, be used to find the antiderivative of a product and a quotient. And you're going to spend like a full weeks on that in Calculus 2. That's a big deal. So, as usual in calculus, sums and differences, no problem. Products and quotients, miserable, a nightmare, terrible. So for right now, let's focus on finding an antiderivative of a function composed of sums of the simple functions. So we can find the antiderivatives one term at a time. X cubed. X cubed, we can find an antiderivative of that separately by increasing the power by 1, bringing it to 4, and then dividing by the increased power. 2x. We can ignore the 2 for a moment, focus on x. Then let's increase the power on x to 2 and divide by the increased power. Sine. What is an antiderivative of sine? An antiderivative of sine is given by negative cosine. Why? Because the derivative of negative cosine returns positive sine. 1 over x is the special case where we have the natural log. Now, what do you think about the constant 3? What's an antiderivative of just 3? There are a few different ways to think about this, and one is to say, okay, I remember that when we calculate the derivative of number times x, the result of that is 3. Therefore, the antiderivative of 3 is equal to 3x. That's probably how I would think about it. So, after just a little bit of simplification, we have concluded that an antiderivative of this function is given by x to the 4th power over 4 plus x squared minus cosine plus 5 natural log plus 3x. But again, I really want to sit and deal with the fact that the situation is much more complicated when instead of sums and differences, you have products and quotients. We know, for example, that e to the x is its own antiderivative, and x cubed is an antiderivative of 3x squared. So if I took that x cubed and that e to the x and multiplied them together, would that be an antiderivative of 3x squared times e to the x? The easiest way to answer that question is to take the derivative of the function capital F and see if the result actually is equal to lowercase f. But because of the product rule for derivatives, this becomes the first times the derivative of the second plus the derivative of the first times the second, which is equal to lowercase f of x plus this entire extra term. this is in no way equal to lowercase f. Which means that no, you cannot find the antiderivative of a product by taking the product of the individual antiderivatives. The problem exists with quotients as well. Let's really see it. If I take the derivative of x cubed divided by e to the x, then I get bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. But even after simplification, even after canceling those common factors of e to the x, I still get nothing that even remotely resembles f of x. I have the e to the x in the denominator, I have the 3x squared in the numerator, but the big issue is that I have this minus x cubed, which lowercase f of x does not. So once again, no, it's just not that simple. F of x is not an antiderivative. That concludes today's material. We started by giving the formulas of antiderivatives for sort of the basic underlying functions, power functions, exponential, trig. Then we saw that if we wanted to take the antiderivative of a sum or a difference or a constant multiple of those functions, that was a relatively straightforward process. We could just do it one term at a time. But as is usual with calculus, the antiderivative of a product and of a quotient is extremely hard to find, and you have to be lucky, generally speaking, in order to be able to find it.